Hey everyone, in this video we are going to learn how to simplify, add, and subtract square root expressions. We will begin with a few definitions, starting with radical, which is the symbol or the notation we use to indicate that we are finding a root. Radicand is the number inside of the radical. And then we have the index, which indicates the root that we are finding. If we are finding a square root, there will be no little number written there. We assume it to be 2 for a square root. If there's a little 3, that would indicate that we are finding a cube root. A 4 would be a fourth root, 5 would be a fifth root, and that pattern would continue. All that changes is how we think about simplifying the root. For square root expressions, they are considered to be in simplest form when 3 things are true. The first is no radicands are divisible by perfect square factors other than 1. So factoring is going to be an important part of simplifying a square root expression. No radicands contain fractions, which we will look at in this video, how to deal with that. And then no square roots appear in the denominator of a fraction. And this is something we will handle in the next video, but I wanted to include here so we had a complete definition. Another term we can see is simplest radical form. And that would mean the same thing. So simplest radical form. If factoring, and even beyond that, factoring with perfect square factors is going to be key in simplifying a square root expression, it would be helpful to have a list of perfect squares to reference. So let's write the first 15 perfect squares. So we'll start with 1, then we have 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. So here are the first 15 perfect squares. Other than 1, these are the values we want to try to factor with. If we need a perfect square that is larger, hopefully it's one that we are familiar with or that would be obvious to us. So let's look at the process of simplifying now. In order to simplify a square root expression, we want to find the largest perfect square which will divide evenly into the radicand. We want to use this to rewrite the radicand as the product of 2 factors, so the factor pair, and then we simplify the square root of the perfect square factor. So our first example is the square root of 80. So we want to factor 80 with a perfect square. So a good strategy that I find works well is to start by finding half of the value we're trying to factor. So half of 80 is 40. So the first factor pair we should think of is 40 and 2. Because if 40 were to be a perfect square, we would be done. That would be the largest possible perfect square factor. But in this case, 40 is not a perfect square. So then we can work down from 40 using perfect squares. So 36 would be the first perfect square that's less than 40. 36 does not go into 80. Now we move down to 25. 25 also does not divide evenly into 80. Then we move to 16. 16 does divide evenly into 80. The factor pair would be 16 and 5. So we write 80 as the square root of 16 times the square root of 5. We simplify the square root of the perfect square factor, so 4 square root of 5. That is the final simplification. Now, what if we chose a perfect square factor, but it was not the largest perfect square? So for instance, here, what if we tried to do 4 and 20? That is a factor pair of 80. 4 is a perfect square. If we simplify, we would get 2 square root of 20, which does not match the answer of 4 square root of 5. But we're not wrong. We're halfway to the final answer. If we look at 20, 20 as a radicand also has a perfect square factor. So if we repeat the process of simplifying again, we would get 2 times the square root of 4 square root of 5, factor pair of 20 with a perfect square. So then 2 times 2 square root of 5 would give us 4 square root of 5, which is equivalent to the first answer. So what does this mean? It means that we want to try to find the largest perfect square factor, that would be the easiest way to simplify the square root expression. But if we only find a smaller perfect square, we can still find the answer. We just need to make sure that we continue the process of simplifying until we are finally done. A good way to think about this is to always check your radicand and make sure that there are no other perfect square factors. So on the left, you check 5. 5 does not have any perfect square factors. You know you cannot continue the process. Where on the right-hand side, when we looked at 20, we noticed that there was another perfect square factor, and we had to keep going. Okay, so let's practice simplifying. So we'll start with the square root of 121. 121 is a perfect square, so we don't need to factor it, we just need to evaluate. So the square root of 121 is really asking what squared is 121, and the answer would be 11. Notice I do not write a square root around the 11 because I have completed the process of finding the square root. Right? To think of a different way, if you were doing an addition problem, 2 plus 3, you get 5. You don't bring the addition sign with you. You don't write 5 plus. We've completed the operation, so the operation goes away and we're left with the simplified answer. So same thing with a square root. If you have a perfect square and you find the square root, now we just have our answer, in this case 11. Now we go square root of 12. 12 is not a perfect square, so we go through the process of simplifying. We can start with that same strategy as before, so take half of 12, you get 6. 6 is not a perfect square, so now we work down. So next would be 4. 4 does divide evenly into 12, so we can write this as the product of 4, square root of 4, square root of 3. Right, the factor pair is 4 and 3. Simplify the square root of the perfect square, so we have 2 times the square root of 3. Now we go square root of 72. Divide it by 2 first, you would get 36. So the factor pair is 36 and 2. 36 is a perfect square. That means it will be the largest perfect square, and we can rewrite 72 as the product of the square root of 36 square root of 2, and then we have 6 square root of 2 as the simplified expression. 54. Half would be 27. That's not a perfect square. So then we go 25, does not divide in evenly. 16 does not divide in evenly. 9, that does. The factor pair would be 9 and 6. So we'd say square root of 9 times the square root of 6, 3 square root of 6. 288. Start by dividing it in half, so that would be 144 and 2 as the factor pair. 144 is a perfect square. Square root of 2, so we have 12 square root of 2. 147. So we'd have 73.5 as half, which is not a perfect square because that 0.5, but we work down, so 64. That does not go in evenly. Then we have 49. 49 does go in evenly. 49 and 3 would be the factor pair. So 49 and 3. So square root of 49 is 7, so we have 7 square root of 3. Let's do a few more. Square root of 51. So half would be 25.5, not a perfect square. 25 does not go in evenly. 16 also does not. 9, no. 4, no. So we've run out of perfect square factors, which means that square root of 51 is as simplified as it can get. So just square root of 51. There are a factor pair of 51, 17 and 3 for instance, but neither of those are perfect squares, right? So they would not be helpful in this process. Okay, so now let's try to go more direct without that whole process. So we look at the square root of 175. So I notice that 25 is a factor. So square root of 25 times the square root of 7, 5 square root of 7. And here, let's just go through the process. Look at the radicand of 7. 7 does not have any perfect square factors, so we know we can't continue any further, and 5 square root of 7 is the simplest version. Square root of 320. So I notice that 64 is a factor. It's 64 and 5 would be the factor pair. and this would be 8 square root of 5. 5 doesn't have any perfect square factors. But let's do this problem differently, just to compare. So let's say you notice 16 was a perfect square factor. So you would say 16 and 20, 4 square root of 20. But what you need to say is, can 20 be factored with a perfect square factor? And the answer is yes. So then you would have 4 times the square root of 4 square root of 5, 4 times 2 square root of 5, which is 8 square root of 5. We get the same answer. We just have a little bit lengthier of a process. And you could have even went 4 here, right? 4 and 80, and done the same process. Square root of 1,300. So I noticed that 100 is a factor. So we'd have 113 as the factor pair. Square root of 100 is 10, so 10 square root of 13. 13 is prime, so there are no perfect square factors. Okay, so now what happens when we have the square root of a fraction? How do we handle that? Well, the first step is rewriting it as 2 square roots. So the square root of a fraction like 1 over 144 is equivalent to the square root of 1 divided by the square root of 144. Now in this case, both radicands are perfect squares. The square root of 1 is 1. Square root of 144 is 12. So this reduces to 1/12. So we can repeat that process with the next example, square root of 225 over 81. So that's equivalent to the square root of 225 over the square root of 81. Both radicands are perfect squares. Square root of 225 is 15. Square root of 81 is 9. So now that we have gone through the process of simplifying, let's move into addition and subtraction. So expressions with radicals are considered to be like terms if they have the same radicands. Often we need to simplify the radical expressions to identify like terms. So when we originally look at a problem, we might not notice like terms until we go through a bit of simplification. So in order to add or subtract radicals, we add or subtract the coefficients of like terms. That is terms with the same radicand. So 2 examples here to motivate us. So we have 3 square root of 5 plus 7 square root of 5. So they have the same radicand of 5. So we can combine them by adding their coefficients. So 3 plus 7 would be 10. So we have 10 square root of 5. Think of the square root part of the expression like the variables when we added polynomials. Or go even further back to basic math. If you had 3 apples and 7 apples, you would add them together and get 10 apples, right? The object would stay the same. So here the square root of 5 comes along. That is our object. Now we have 13 square root of 10 minus the square root of 10. So the radicand of 10 means we have like terms. So we combine the coefficients. So 13 minus 1, right, there's a 1 there, would be 12 square root of 10. Okay, so now we move into problems that are going to combine both pieces. So first we have square root of 28 plus square root of 63. Looking at it right now, they are not like terms. But let's see if we can simplify both expressions and see what happens. So the square root of 28, we can write as the square root of 4 times the square root of 7. 63 can be the square root of 9 square root of 7. Simplifying the perfect square radicals, we get 2 square root of 7 plus 3 square root of 7. Now we do have like terms. We combine their coefficients to get 5 square root of 7. Next up, we have no like terms, at least it doesn't appear that we have like terms. So we start by simplifying. So 60 would be square root of 4 square root of 15. Square root of 121, well that's a perfect square, so that would be 11. And then 3 square root of 15. 15 has no perfect square factors. So we have 2 square root of 15 plus 11 minus 3 square root of 15. So we have 3 terms. Only 2 of them are like terms, the terms with the square root of 15 in them. So we combine those 2 terms. So 2 minus 3 gives us negative 1. And we wind up with 11 minus 1 square root of 15, or 11 minus square root of 15. We can write it either way. Next, same thing. We look, none of the radicands are the same, so we start by simplifying. So we have 3 times the square root of 16 square root of 2 minus 2 times the square root of 4 square root of 2 plus the square root of 64 square root of 2. So we have 3 times 4 square root of 2 minus 2 times 2 square root of 2 plus 8 square root of 2. So 12 square root of 2 when we multiply those coefficients there, minus 4 square root of 2 as the middle term, plus 8 square root of 2 as the last term. Now all three are like terms. We can combine their coefficients. So 12 minus 4 is 8, plus 8 is 16, and we have 16 square root of 2. Our last example, now we have 4 terms. Again, looking at all their radicands, none of them are the same. Doesn't seem like we have any like terms, but we can simplify all 4 of these. So we have 8 times the square root of 9 square root of 3 minus square root of 4 square root of 5 for the 20 minus 2 times square root of 25 square root of 3 plus the square root of 100 square root of 5. Then we get 8 times 3 square root of 3 minus 2 square root of 5 minus 2 times 5 square root of 3 plus 10 square root of 5. We have to simplify some coefficients here. So 24 square root of 3 minus 2 square root of 5 minus 10 square root of 3 plus 10 square root of 5. So we have 2 pairs of like terms. So the 24 rad 3 minus the 10 rad 3. And then the other 2 terms both have square root of 5. So this would give us 14 square root of 3 plus 8 square root of 5. So the key for this whole video is being able to simplify a square root expression. Once we are comfortable with that, then we can progress into the addition and subtraction by identifying our like terms, often through simplifying, and then combining the coefficients with either addition or subtraction. So make sure you practice with this before moving into the next video.